Okay.
Yeah. I think I'll just introduce. Thank you, everyone. Thank you, everyone, for joining in. Today we have Jessica from MIT presenting her research work. And on behalf of IEEE PELS IES Society and Women in Engineering Bangalore section, I welcome Jessica, and hopefully this will be beneficial to everybody. Please go ahead, Jessica. Please go ahead with the presentation.
Great. Thank you so much. And thank you all so much for having me. I'm looking forward to getting to share some of my work and discuss with you all and learn a little bit more about what you do as well. So for those who aren't familiar, I'm in California right now, and so good morning for me, but I know it's good evening for you all. All right, power electronics are building blocks for processing electrical energy. Here I'm showing a variety of things that affect our daily lives, where we can go, who we can talk to, how we can live. And all of these are critically dependent on power converters. Now, one big focus of the power electronics field today is figuring out how to make the converters inside of these things much, much smaller. A smaller converter has many advantages, including lower cost and a wider realm of potential applications. Let's see. Having a little bit of issue moving forward.
Oh, it's not changing to the next. Start changing to the next slide. Yeah.
Okay, perfect. Now, I imagine most of you are familiar with the concept of a power converter, but I'd like to briefly review it because it motivates a lot of the reason why we do this work. At its root, a power converter pulls energy in from a source. It momentarily stores it in some sort of energy storage, and then it delivers it to a load, typically in a different voltage or a different form. Now we control this process with switches, and it's cyclical, so we do it thousands or even millions of times per second. Now, whenever we start to think about making converters much smaller, we care about power density, which is the amount of power we can deliver to the load divided by the volume of the converter itself. And in order to achieve high power density, we also need to achieve high efficiency. That way we can handle our losses thermally at high power density. Now, if we take a look at the inside of a converter, we find that a large proportion of the volume is actually taken up by this energy storage. I'm going to highlight that in a MacBook charger you see here. Typically in inductors, typically in converters, we use inductors and capacitors for energy storage. But there's nothing that says we have to use inductors and capacitors. In fact, magnetic components like inductors and transformers scale down pretty poorly with volume. So we'll look at that a little bit more closely. If we were to calculate a maximum power that an inductor, for example, can handle, we might assume a maximum flux density limit. We might also assume a maximum current density that can go through the copper for the inductor. And assuming both of those, the maximum power that this inductor can handle is actually proportional to the product of the core area and the window area. So that's length dimensions to the fourth. And so what that means then is if we take that inductor and we scale it in all three dimensions by scaling factor epsilon, our volume is going to increase by epsilon cubed. The maximum power that this inductor can handle is going to increase by epsilon to the fourth. That means just a small increase in volume gives a drastic increase in power. Now that's a great thing for high power applications. But if we look at this in the reverse direction and we try to scale down our volume, we find that the maximum power decreases much faster, meaning power density drops. And that's counterproductive for miniaturization. So to enable major advances in power density going forward, we're going to have to figure out a different way to store energy in power converters. So this is taking a step back and thinking, well, how can we do this completely differently than we do it today? And one promising alternative then is piezoelectric energy storage, and that's what we've been looking into. Piezos rely on the piezoelectric and inverse piezoelectric effects, which essentially means that when we apply a voltage to its terminals, it induces mechanical stress and strain in the material. and vice versa. So through that process, we can strike mechanical resonance, like this animation you see here. And whenever the piezo resonates, it stores energy in mechanical compliance and inertia, somewhat like a mechanical spring. Now, piezos are attractive from the standpoint of they have planar form factors. They may be more amenable to batch fabrication than magnetics. They can even provide isolation with multi-port resonators. But perhaps most importantly for our purposes, they have very high power density capabilities and very high quality factors. If we take a look at some work that has come out of Dartmouth College, this work is comparing the power transfer capabilities of a variety of different energy storage units and power converters like the piezo, LC resonators, even capacitor dielectrics. We find that the potential power handling capability of a piezo might exceed that of even capacitor dielectrics. Now, this calculation is very idealized, but if that's true, that's a big deal. Now, piezos have been used in power converters previously for lighting electric lamp ballasts through piezoelectric transformers a few decades ago. Since then, most of those have been replaced by LEDs, but that is one way in which they've been used. They've also been used in some energy harvesting circuits, which you see in this shoe here on the right. But overall, piezos have seen very little use in power conversion, especially compared to magnetics. And many attempts to use them in research without magnetics have shown pretty limited performance. But that being said, the best ways to use a piezo in a power converter are yet to be explored, much less the full realm of possible ways. So that's the exact question we're going to poke at today. How can we best use a piezo in a power converter? Now we're going to start attacking that question by going through what are the various switching sequences and topologies that we can use for a piezo in a power converter. Once we figure out what those could be, we then would like to constrain those for highest efficiency so we can analyze and compare them. And then after that, we'll start to look at, well, what are some initial experimental results with a piezo in a converter, and what are those telling us? And then finally, we'll wrap up with what are some unanswered questions for piezo-based converters going forward. So to start, before we can design a power converter, we first need a model for the piezoelectric resonator. So for this, we typically use what's known as the Butterworth-Van Dyke model. It's got a physical capacitance between the piezo's two electrodes, and that's in parallel with an LCR branch. And that LCR branch models the piezo's mechanical resonance properties. So the L, for example, models its inertia component, and the C models its compliance component, again, similar to a spring. Typically in resonators, we see a much larger inertia component, meaning the inductor is much larger than that capacitance. So now that we have a model for our piezo, we can start to think about what would we like to have in a piezo-based converter. Well, if we believe piezos could be our route to high power density, we'd like to use them without any additional magnetic energy storage. So we'd like to use it all by itself in this source load system we're showing here on the right. In addition to that, we'd like to always soft charge CP. And what we mean by that is we'd like to always charge and discharge CP through resonance so we can reuse the energy it stores rather than lose it. In addition to that, we'd like the converter to be capable of voltage regulation, which means we'd like to be able to span a wide range of input and output voltages with high efficiency. And for practical reasons, we'd like the required switch implementation for this converter to be as practical as possible. So maybe as few switches and as simple as possible. Now, keeping all of these in mind, we can start to enumerate then different ways we can connect the piezo to the source load system. And we're going to refer to each of those connections as a possible stage of a switching cycle. So we'll start with what we call connected stages, which essentially mean that we're going to connect the piezo to the source load system with its terminals such that the voltage across it is some combination of Vin and Vout. Now, these are our energy transfer stages. So during these stages, energy is going to be coming in from the source, and it's going to be delivered to the load. Now, in addition to that, we could also have what we'll call a zero stage, in which we short the piezo's terminals. Now, the reason why this is useful is it allows the piezo states, that inductor and that capacitor energy storage, to exchange energy. So we'll use the zero stage to pull some of the energy that was in the inductor into the capacitor, for example. And then finally, we could leave our piezo open circuited. And so the reason why this might be useful is it allows the piezo's capacitance, parallel capacitance, to participate in that resonance. And so through open stages, we can charge and discharge that capacitance to different voltages. And that's important for the soft charging we just mentioned. We're going to refer to this as an open stage. So now we can start to string these stages together into what we call a switching sequence. And so this, we can think of a switching sequence as the specific order of stages across the switching cycle that we repeat over and over again to pull energy in from the input, store it, and deliver it to the output. Now, our goal with this switching sequence, again, is to soft charge CP at every stage transition. And so that means we're going to have to alternate the connected and zero stages where VP is fixed with open stages where VP can change. And so that's why in this example sequence you see here, we alternate those connected and zero stages with open stages. So let's take a closer look at this example sequence. Let's say our first stage is Vin minus Vout. In that first stage, we're going to pull energy in from the source. We're going to momentarily store it in the piezo and also deliver it to the load all at the same time. At some point, we'll turn that stage off and we'll have what we call an open stage again. And so in stage 2, with an open stage, because IL is still positive, it allows us to discharge CP all the way down to 0 in time for stage 3, at which point VP equals 0. So during stage 3, we'll allow those states to exchange energy. And at some point, when IL becomes negative, we might start then stage 4. With a negative IL now, we're able to charge CP all the way back up to Vout, at which point we will begin the 5th stage. This Vout stage allows us to deliver energy to the load. And then finally, we'll use the remainder of the cycle to cycle CP back up to the original Vin minus Vout, and we'll repeat the process. Now we're going to refer to these stages, or switching sequences, excuse me, by the order of their connected stage voltages. So we'll call this sequence Vin minus Vout, 0, Vout. And this is going to be our example sequence throughout this talk. Now, we might ask the question then, well, what are all the possible switching sequences we could use in a piezo-based converter? So we're going to enumerate these with the constraining assumptions you see here. We'd like to have a minimum number of stages for simplicity. We'd like to connect to both the input and the output, like a converter has to, at least once each. We must have at least 2 connected stages to balance the energy on the piezo from cycle to cycle. And we'd like to alternate connected and zero stages with open stages again for that soft charging. Now, enumerating all the possibilities that satisfy these criteria gives us 7 4-stage sequences and 33 6-stage sequences. Now, we've said nothing about how practical these sequences are. We've only enumerated them out at this point. So that's exactly what the next step here would be, is to down select these sequences to what's actually practical for power conversion. So our first step in doing that is we've down selected for sequences that can be completed in 1 resonance cycle. That allows us to avoid excess charge circulation. Then we make the step of down selecting for piezo-based converter sequences that can regulate voltage, meaning they give us a wide range of input and output voltages. And that step actually eliminates all of our 4-stage sequences. There are no 4-stage sequences that can regulate voltage. And then finally, we make an additional practical step and constrain for sequences that can be realized with just unidirectional blocking switches. And so by that, I mean, we'd like to keep 4 switches that block voltage in one direction. So one example is that top topology you see where there are 4 independent switches. And another example could be the bottom topology where we've actually got 3 switches, but one of them blocks voltage bidirectionally. And so that bidirectional blocking switch needs to be implemented with 2 unidirectional blocking switches. Going through this entire process leaves us with 5 6-stage sequences that can be realized for both step down and step up versions. Now, some of these sequences can be realized with only 1 practical topology, but some of them could be realized with 3. And so again, we're focusing on what's the sequence that we're cycling the piezo through rather than the topology. Now, all of these sequences, again, meet our goals of requiring only piezo for energy storage, no magnetic components. They always soft charge CP, and they're capable of voltage regulation. And so these sequences then can be realized in 9 topologies, which I'm showing here just to show the variety of topologies. Some of these look like switch capacitor converter topologies. Some of them look like resonant converter topologies. Now, one thing that I will point out is some of them have 2 changing nodes, one at the input and one at the output, and then some of them have only 1 changing node, and this will actually have implications for soft switching, which we'll talk about later. So from here, we've listed out all the possible switching sequences and topologies we could use for a piezo-based converter. But now we'd like to constrain those for highest efficiency. That's what's going to make them competitive at high power densities, especially with other designs. Now, efficiency is typically the biggest constraint when we're choosing a topology. So we might like to constrain for additional behaviors besides soft charging. All of our switching sequences are already capable of soft charging. We know that. We'd like to also maybe constrain for all positive instantaneous power transfer, which means at no point in the cycle are we going to be delivering energy back into the source or pulling it back out of the load. We only want positive power flow at all times. We might also constrain for soft switching on all of our switches. In real life, many of us know that switches realistically have capacitance across them, just like the piezo does. And we would like to reuse the energy that that capacitance stores rather than lose it. So we're going to resonate the switch capacitances to 0 volts before turning the switch on. And so we call that zero voltage switching, or ZVS. Now, in order to constrain the piezo's behavior for high efficiency, we first need to know a little bit more about how it works. So we're going to look at an example sequence here. This sequence is the same one we've been looking at, Vin minus V out, 0 V out. We're going to look at it for the case where V out is a little bit less than half of Vn. And this sequence itself can be realized with the topology you see here. This topology can be realized with 2 active switches and 2 passive switches or diodes. And that's a pretty practical topology. So to understand what's going on inside the piezo, we're going to plot its states against each other on what we call a pair of state planes. And so on one plot, we'll plot the inductor current versus capacitor voltage. And that's the piezo's voltage as well. And on the plot on the right, we're going to plot the inductor current versus that resonant capacitance. And this is going to give us a good idea of what's going on stage by stage. And so if we start with stage 1 in our Vn minus V out stage, we know we're pulling energy in from the source and we're also delivering it to the load. But Vp is fixed at Vn minus V out. And so that's going to give us the state plane trajectory you see here, where our inductor current is rising, Vp is staying constant, it's fixed at Vn minus V out on the left state plane. But on the right state plane, we see IL resonating with Vc. So even though the piezo's terminals are fixed, IL is still able to resonate with Vc. Now from here, eventually we'll stop this stage, we'll begin our next open stage in which If IL is positive, it's going to enable VP to decrease all the way down to 0. That's for our soft charging. At that point, we'll begin our 0 stage, again, allowing energy to circulate within the piezo states. Let's say we do this until the inductor current reaches 0 again. At that point, we've reached half the cycle. We've completed half the cycle, and so you see what looks like a half circle on the right state plane. With the inductor current negative, we can then charge VP back up to V out, at which point we'll begin our stage 5, V out. This is another energy transfer stage where we're transferring energy to the output from the piezo. And then finally, we'll use the remainder of our cycle to charge CP all the way back up to V out again. And we'll repeat this over and over and go around these state planes many, many times. So finally, we're back where we started, in the same exact place. And the fact that we've arrived at the same place where we started means we've constrained for periodic steady state. That's a good thing for converters. Another thing we've constrained for is soft charging. We've always resonated CP to its next stage voltage before that stage begins. And if you look closely, you would also find that we've constrained for all positive instantaneous power transfer. These are high efficiency behaviors. Now the state plane on the left gives us good insight into what's going on in terms of how the piezo interacts with the source load system. But the state plane on the right tells us where we are in the resonance cycle. And so we can actually use the proportion of the time used up by each stage to calculate our switching times. Now, say we want to constrain for 0 voltage switching on all of our switches in addition to the soft charging. We can use the state plane to see how we would need to modify the switching sequence to do that. So in this particular case, we needed to modify the 6th stage, that's an open stage, to swing VP all the way up to Vn at 0.6B on that plot there to achieve soft switching. Now, the reason why we care about the state planes is they give us a good idea of what the time domain waveforms would need to look like. On the state plane, we've numbered all the stage transitions. These correspond to the numbered dotted lines on the time domain waveforms. So in an experimental setting, for example, if we can only measure VP and we can't measure the internal states of the piezo, we can still have a pretty good idea of what IL and VC are doing based on how VP changes, whether it's increasing or decreasing, and its slope when doing so. That's how we know we've constrained for these high efficiency behaviors. Now, everything up to this point on the state plane has been purely qualitative. But if we'd like to solve for where these actual points are on the state plane and calculate our actual switching times, we would need to solve for a periodic steady state solution. Now, solving the entire system of the piezo across 6 stages is very complicated, especially if we consider the resistance. But if for a moment we assume our piezo is ideal, we can actually do this pretty simply with a system of 9 equations that MATLAB can solve pretty well, or Python, or whatever we use. Now, we can do this then using only the stage transition point states. And so what is IL at the transition point? What is VC at the transition point? We can relate all of these transition points by conservation of energy and conservation of charge. And so that's applicable for our connected and 0 stages as well as our open stages. That governs the laws of how the piezo has to operate in order to maintain the same cycle to cycle. In addition to those, we can constrain our IL 0 crossings for all positive instantaneous power transfer and solve exactly what those switching times would need to be. All right, so at this point, we've constrained for high efficiency behaviors, but how can we estimate what the efficiency is itself? Again, we would rather not solve the whole system of equations with differential equations, et cetera, including the loss. So we would like to find a way to estimate it. And our first step in doing that is going to be assuming IL is sinusoidal. So if we assume IL is sinusoidal, which is a pretty good assumption considering Piezos have a very high quality factor. We can then calculate, well, what's the total charge transfer in each stage? So we look at this from the perspective of, if the piezo has a certain amount of charge to deliver to the load, what does it have to transfer in each stage? And so for connected and zero stage charge transfer, the amount of charge that needs to be transferred is equal to the energy out, that's P out divided by the frequency, also divided by the voltage. So that gives the charge transfer out. We're also going to divide by a K factor, which we'll consider a charge transfer utilization factor, which means how much of this charge transfer in the piezo are we actually transferring to the output? And so just to show briefly, if we take our example sequence with Vn minus V out, 0 V out, to calculate K, we would say, well, what's the stage 1 and stage 5 charge transfer, because those are delivering energy to the output, divided by the total charge transfer during all connected and zero stages. Now this actually ends up being just a function of Vn minus V out, but the K value varies from switching sequence to switching sequence. All right, so from here, we've calculated connected and zero stage charge transfer. Now it's time to calculate the open stage charge transfer. And essentially the open stage charge transfer is just the transfer needed for a round trip for CP to its highest voltage and to its lowest voltage. And that'll give us what the charge transfer needs to be during open stages. Now, once we've calculated this charge transfer, we can add it all up and set it equal to the integral of IL. And if we're assuming that IL is sinusoidal, this can then give us an equation for what the amplitude of IL is. And so this equation for the IL amplitude has a connected stage term, that's the first term, as well as an open stage term, that's the second term. And what's useful about this is it tells us information about the amplitude of the piezo's resonance. So how high is the piezo resonating? And so we can use that then to estimate what the piezo's efficiency would be. And again, this is much simpler than having to solve the entire system. And so as engineers, we like an estimation technique like this. Now, if we plot out the efficiencies of all the different switching sequences we've enumerated, we actually find quite a bit of variation between them. Some of them achieve efficiencies that are pretty high, and some of them are pretty low. We find that the highest efficiency sequences tend to spend a larger amount of time transferring charge to the output, rather than just circulating it inside the piezo. And so that refers to what we just discussed a moment ago. They also spend less time in stages like zero stages, as open stages, for example. So they use the piezo more effectively, and that means a lower amplitude of piezo resonance delivers the same energy to the load. Now, if we look at what happens when we constrain for the soft switching, like we mentioned, that's the zero voltage switching, we see a slight efficiency drop. And this is because of additional charge transfer required during open stages to swing the piezo's voltage all the way to what it needs to be for soft switching. Now, I want to emphasize that this is just the piezo's efficiency. We have not considered the possible efficiency rise then for the switches. And so that's a trade-off that would need to be evaluated by the designer. Okay, at this point, we've figured out how do we constrain for high efficiency and estimate efficiency. So it's time to build a converter. We figured out which sequence is going to be the most promising for a piezo-based converter. So now it's time to validate it. Now our first step in validating this is to acquire a piezo itself. And it actually turns out that piezos are a little bit difficult to source, but we were able to find some samples from a company called APC International and some others from PI Ceramic, for example. Now in our first prototype, we were interested in just a low frequency design for ease of initial demonstration. And so in the world of small miniaturized electronics, we tend to go to high frequency. And so 100 to 300 kilohertz is actually considered low frequency for us. We also sought a piezo with a high mechanical Q material. Now the quality factor is something that's regularly used to judge piezos, but also magnetic components. And so that's something we were looking for when choosing a piezo, because it means higher mechanical efficiency. So we acquired several different piezos. We hooked them up to a network analyzer to see what their impedances look like. And so a classic thing about piezos is they have a resonant frequency, which is the low impedance point, but they also have an anti-resonant frequency, which is the high impedance point. And so those are essentially just the series combination of L and C resonant frequency in the mechanical branch. That's the resonant frequency. And then the anti-resonant frequency is when the CP is also resonating with L and C. And so it creates a very high impedance point. With both of those points, we can extract what the parameters of the Butterworth-Van Dyke model would be for that specific piezo and figure out which one is best for our purposes. And the piezo that we found to be best for our purposes now is a disc-shaped piezo made by APC International. It's from a modified PZT material. PZT is very commonly used in piezos. It stands for lead zirconate titanate. And so energy harvesting, a lot of different applications PZT has been used for. It has a radial resonant frequency of 113 kilohertz. And so what I mean by radial is the piezo is actually expanding in the sideways direction radially. So it's not vibrating up and down like the initial animation, it's vibrating outward along its radius. And so with this piezo, we've assembled a pretty simple prototype. It's just a 2-layer board. We've used GaN FETs for our MOSFETs, and we've used Schottky diodes for our diodes. And everything I'm about to show you here is an open loop operation. And so we've manually tuned each of these points for the behaviors we want. Now, when we operate this piezo-based converter experimentally in the real world now, we get waveforms that match very closely what we hope to see. Now, this is great news for being able to operate these piezo-based converters with the high efficiency behaviors we want. And so with these behaviors, you see soft switching, which means the 2 switch nodes have resonant transitions between their low points and high points. And so you see VS1 and VS2 slowly resonate up to each of those for 0 voltage switching. We also see soft charging of the piezo, which means that the piezo itself also has resonant transitions. And if you looked closely, you would also find that the piezo is exhibiting all positive instantaneous power transfer like we desired. And the result of these high efficiency behaviors is this particular point I'm showing you has an efficiency above 97.1%. Now you'll see that the voltage here is just about 100 volts to 40 volts, but the power is pretty low. And so it turns out that piezos shine better in applications that require the high voltage and low power. And I'd be happy to discuss more why later if that's of interest to you. Now, if we take a look at our experimental waveforms and see how they change with different operating points, we find that it's actually this 0 stage that allows us to regulate voltage. And so in that top waveform, I'm showing an operating point where the output is almost half of the input. It's very close. And because of that, the 0 stage is almost non-existent. But as we decrease the output voltage, or increase the input voltage rather, so we decrease the ratio, that 0 stage increases in length. And so you see in the bottom plot where our ratio is much lower, that 0 stage is much more dominant. This is how we achieve voltage regulation of the output. Now, as we increase power, we see our connected stages become much more dominant. So in this top waveform, I'm showing a very low power point, and because of that, our switching cycle is almost all open stages. But as we increase power, we see those connected stages become much more dominant. Now, if we take a look at how this gain of the converter changes with frequency and load, we find that as we increase frequency, the gain and power level go down. And so the reason for that is we're operating the piezo's inductive region. We're operating between those 2 resonant and anti-resonant points. And so what I want to note here, though, is this is not purely frequency regulation. We have to regulate other things too, like duty cycle and dead times. But this does give us a good idea of how we might operate this. And another thing that I'll point out here is that you see some jagged lines in this gain plot at about 120 kilohertz and about 122 kilohertz. These are actually discontinuities in the gain curve due to what we call spurious modes. And so that's stray capacitance in the resonator that's participating in resonance. And that's something we don't want to happen, but it contributes slightly to some efficiency drops we'll see later. But that's outside the scope of what we're studying here, but it is interesting to point out. Now here, when we plot out what happens as we vary voltage conversion ratio and power, we find that we can achieve a pretty wide range of low power levels that can give us good performance. But as we scale down our voltage conversion ratio, we find that our efficiency scales down as well. This is something we were able to predict with our efficiency curve, with our efficiency calculation earlier. But what's interesting is if we're at a voltage conversion range above 0.5, our efficiency does not vary at all, voltage conversion range. And so this gives us essentially a free conversion range of 2 with no penalty in efficiency. And so you can imagine if this converter were used as a regulation stage, it could do that with very high efficiency across a gain range of 2. Now, if we would like to increase our power handling capability, we can do that by increasing the piezo's voltage, the converter's voltage. And so what we see here is the power that can handle high efficiency increases as we increase the voltage. So that would tell us that it's actually the piezo's current that would be limiting us in terms of the power that we can handle. And then finally, I want to show the efficiency as a function of frequency. And the reason why this is interesting is because it shows us that for the same gain, even as we scale voltage and power, we get the same efficiency at the same frequency. Also notable on here, as you can see, the efficiency drops at the spurious frequencies that I just mentioned earlier, the reasons for the discontinuities in the gain curve. And so again, these are not desirable. They're a function of the piezo's manufacturing as well as how we've mounted it. But that's something for study on a later day. Okay, so at this point, we've demonstrated that we can produce a converter based on only a piezoelectric resonator. But there's many unanswered questions going forward that we're going to have to answer to make them practical. So first off, well, what's the best piezo? How do we choose a piezo geometry? How do we choose a piezo material? How are we going to control this piezo-based converter for all the high efficiency behaviors we want? We'll actually zoom into that a little bit more closely to show that we do have to modulate frequency, but we also have to modulate dead time and the pulse width. There's only one solution that will give us all the high efficiency behaviors we want. So that's pretty difficult and pretty challenging going forward. In addition to that, what's going to happen as we scale up power? Or what's going to happen as we try to scale up frequency? It turns out that as we decrease the size of our piezo, its frequency goes up. So you could imagine that this is something that we would need to implement for high power density, but the challenges of accommodating higher and higher frequency would have to be overcome. And so this is another thing that we'll have to look into to see how practical these would be. And then what would happen in terms of integration? Is it possible to integrate piezos? Or how would we deal with high step up or step down ratios or even isolation? It actually turns out that 2 of these can actually be accomplished with what we call piezoelectric transformers. And so piezoelectric transformers, again, have seen use in power conversion for the fluorescent lamps, but they might have a much wider range of potential applications than just that. And so essentially what we've done here is we've got electrodes on the piezo just like normal, but we're also tapping the piezo at a different dimension of vibration. So you can see that along that long end from left to right, the piezo vibrates much more widely than it does up and down. And through that process, we get a voltage conversion ratio that has an ideal voltage conversion ratio in the piezo transformers model, which you see in the lower left-hand corner. So just like the piezo resonator, the piezo transformer has an LCR branch for its mechanical resonance properties. It's got capacitances at its terminals. But again, the advantage here could be the inherent isolation as well as the voltage transformation. So with that, we can conclude that we can design a converter based on a single piezo with all of the high efficiency behaviors we've discussed, like soft charging, zero voltage switching, voltage regulation, all positive instantaneous power flow. And we can do this with practical switch implementations. And that's what's going to help make these competitive against other types of converters. Now, the take-home point here is that it's actually the effective utilization of this piezo, meaning all of these behaviors together, that enable the competitive performance with no additional energy storage components. And so with that, we can conclude that these are promising for high voltage, low power applications, but additional development is needed to really get them to where they're competitive in terms of miniaturization. But all in all, we are optimistic that these may open new application spaces for power electronics, such as in spaces where magnetic components can't go, or where we need ultralight applications, for example. So with that, I'll wrap up my technical part of the talk, and I'd be happy to open up to Q&A, or I can also answer some of the questions that you sent me. Which do you think would be best first?
We'll take some questions first.
Okay.
Maybe some might get answered. Thank you very much. Very good presentation. Especially that state plane to waveform mapping was very cool. Very good. Thank you. Thank you for such a detailed presentation. We'll take one question. What is Raghavan has asked, what is the basic difference between dielectric resonator and piezoelectric resonator? And is there any comparison between them?
So by a dielectric resonator, are you talking about an LC resonator, like with the capacitance? Is that what you mean by that?
Raghavan, are you here? Can you unmute yourself and go ahead? Yes, yes. Please let us know if it's like a LC resonator.
Yes, sir. Yes, sir.
Yeah. Yes, okay. That's exactly what it is.
Yeah. So I think the main difference is with the LC resonator, you're still storing energy in the capacitance and the inductance of that resonator. Whereas with the piezoelectric resonator, you're actually storing energy again in the mechanical properties, the inertia and compliance. And so in terms of power density, I think both could be competitive. It'll be interesting going forward to see what happens with LC resonators as well. In fact, there is some work being done on that, not by us, but by some other people. But yeah, that's a great question. It'll be interesting to see going forward.
Good. Thank you. Any other questions? Okay. Meanwhile, I had one question. When you say vibration and when it is moving, let's say circular, radially, what is happening in the physical property? How is it able to do that? Like, what is the physical essence of it expanding radially? Is there? What is the phenomenon? Yeah.
So it ends up just being a, so you might remember when we plotted, actually maybe I can go back to it. When we plotted out the impedance of the piezo on the impedance analyzer, you actually see many different resonant components. Let's see, maybe I'll jump back.
Yeah.
Oh, too far. Sorry. Okay. So looking at this impedance plot, there are actually many different resonant points. And so those, you can think of it as we're exposing the sides of the piezo to this voltage that we keep striking it periodically. And that can still induce resonance in the perpendicular direction. And so there are different properties for striking a perpendicular direction versus a parallel direction. Typically, piezos can strike the parallel connection better, but the perpendicular still works. And so the dipoles inside the piezo itself can still resonate then in the perpendicular direction if we strike that resonant frequency.
Good, very good.
Does that answer your
Dr. Nali? Yeah, yes. Because I was just curious about the material properties, actually, what is happening. But yeah, I understand the concept. Yeah. Dr. Lalit, please unmute yourself and go ahead.
Hello, can you hear me?
Yeah. Please go ahead.
Yeah, first of all, thank you very much. It was an excellent presentation. I really enjoyed it. My question is about the fact that we moved from an electrical resonance phenomenon to a mechanical resonance phenomenon. What are the implications in terms of the aging of the device itself? Can we go up to the same amount of number of times we are storing and removing energy from the piezo system as compared to, let's say, LC system?
Yeah, that's a really good question. So we have not personally studied the reliability over time of this yet, but that's a really important question going forward to make them practical. So when a piezoelectric resonator is fabricated, it is put through what's called a polarization process, which is where we expose the material to very high voltage. And so we, in that process, make the dipoles align in one direction. So we polarize the dipoles to align in one direction. It's possible that over time that starts to relax. And if it does relax, then we start to lose some of our piezoelectric properties. Now, I don't know, I have not observed or studied this myself. This is just, forecasting out what I would expect to happen. And so that's a very important question going forward. That question about the losing the polarization, but also does it become more susceptible to cracking, for example, over time? And so because it's a ceramic material, once it cracks, it's done. There's no going back once it cracks. And so it'll be interesting to see, what can be studied about that going forward, for sure.
Okay, thank you.
Dr. Lalit, please introduce yourself so Jessica knows your background.
Hello, Jessica. I'm Lalit. I'm currently a power electronics engineer at CERN in Geneva.
Great.
I design radiation tolerant power supplies. So yeah.
Oh, very cool. Thank you so much. Nice to meet you.
Yeah, same here.
Thank you, Dr. Lalit. Chetan Raj, you can just unmute yourself. Chetan Raj asks, can you go to the impedance characteristics? Yeah.
This one on the slide.
Oh, okay. Yeah, the question is whether, please go ahead.
Yeah, that impedance characteristics, whatever they are shown in that Bode plot. So across a wide number of frequencies, what is the impedance characteristics, whether it is purely resistive or inductive? So how it will affect the efficiency of your this thing?
So you're asking how the impedance characteristic is going to affect the efficiency?
Yeah.
Okay. Yeah. So if we take a look at this dominant resonant frequency here, this is the radial mode frequency. At the bottom point here, we should be reaching something very close to what the true resistance is inside that mode. And so once we know what that resistance is in this Butterworth-Van Dyke model right here, we can start to estimate what the efficiency would be, and we need that to be as low as possible. But what's interesting about this, and this is kind of difficult to explain sometimes because we're so used to just thinking about, resistance is what we need to be low. We actually are interested in what's the ratio between the characteristic impedance of the resonance and that resistance. Because you can imagine that if L is so much larger than C, we're going to have less current flow, but more voltage across this capacitance here. And so if we have less current flow through that resistance, we have lower loss. So even if the resistance is higher, if we have less current flow through it, then we can deal with lower loss, which is helpful, or even the same loss. And so it's a really good question. I'm happy you asked it because it's not as simple as just minimizing the resistance. We also have to think about what is the characteristic impedance of that LCR branch. And so just to give some more details here, this is our radial mode resonant frequency. This one would be our thickness mode resonant frequency. And so that means if the piezo is vibrating up and down, what the resonant frequency would be there. And then I imagine above that, we're just getting into higher harmonics of each of those resonant frequencies. And so that's something we would perhaps want to compare between all of those one day is what's the difference between the resistance and the characteristic impedance.
Okay, thank you, madam. Thank you.
Okay. Thank you. Okay. Ramji Sharma, can you unmute and go ahead? Okay, Ramji Sharma asks, how do you maintain electrical connection when you have such a vibrating component? Or how do you maintain electrical contact?
Yeah, so this is a picture of a disc piezo right here. And so this entire surface is actually deposited with silver. And so inside here we have the PZT material, but on top, this entire electrode is silver that has been deposited onto the piezoelectric material. And so that silver is actually our electrical connection. In terms of as it vibrates, it actually vibrates in a way that we can't see. It's very small. It's a few microns, for example. And so it is a mechanical connection though, and there is vibration. And so that's something interesting going forward too, is how can we keep the connection as we need it to be in a reliable way. We can, let's see, let me jump to our prototype here. We just had the piezo standing up like this, but this is not practical for commercial converter. This was for validation purposes. Because it was standing up like this, it could vibrate freely, but what if instead we have it sideways and we have it connected down onto the board? What implications does that have for its mechanical movement? So that's a great question. Thanks.
So is that a purely research problem, or is it just a mechanical structure kind of, like you just change the configuration, or is it a pure research problem?
I think that could be, like you said, just a mechanical structure problem that will need to be solved in the engineering world before these could be widely commercialized.
Okay. Yeah. So now Kartikeya, yeah, he's asking how does this fit into when we use high voltage converters? How does this entire setup fit into that configuration? That is what Kartikeya, can you unmute yourself? Is that what you're asking? Yeah, maybe he's on the desktop or something. Yeah, so the fundamental question is, how does this setup fit into a high voltage converter?
And so high voltage,
Jessica, can you hear me?
oh
Yeah. Go ahead, please.
Yeah,
go ahead.
Hi. I was asking this question in the context of some of the research that Dr. David Perrault has done at MIT. Especially in the context of one of his papers that I read back in 2019, which discusses the details on electroaerodynamic propulsion.
Yes.
Something that he has done, and I specifically read that because my research is mainly based on designing hybrid DC converters for satellite propulsion systems. I work at Missouri S&T satellite design team. Currently, I'm a PhD student at Rolla. So I was always interested to know how these high voltage DC-DC converters can add the functionalities of these piezoelectric transformers, because we were always running into issues of fitting those transformers and the inductors within the space constraints we had, and we had to stick and conform to these PC104 standards for our PC104 standards for conforming to the size constraints of our nanosat program, and we always used to run into issues of how can we use size of these inductors, and piezoelectric transformers definitely looked as one of the Anderson race, but I never really could
Yeah, I think it got cut off, but I think you got the gist of. Yeah. Please go ahead. Yeah.
Certainly. Yeah. So that's a fantastic question, and that's actually a question we've also been asking a little bit. Is what could happen in terms of how could this be used in the really high voltage pieces? And you're right to think that for anything flight related, something that is not as heavy as a magnetic component could be certainly advantageous. And so where we think the piezoelectrics would shine the most would be in the low power range for those. So think, really small type things. For the very large things like satellites or whatever it be, I believe as of right now, the magnetic components are still going to win. It just depends on how high of power you're hoping to achieve. Now, that's not to say that the piezos couldn't one day, but again, that scaling property with the magnetic component, as we go up in power, a high increase in power is just a small volume increase, which is good at high power applications for magnetics. So if it's high voltage, high power, I think the magnetic solution is probably going to win. If it's high voltage, very low power, I think the piezoelectric transformer could certainly compete pretty heavily.
Yeah, because the power range I'm talking about is around. So the converter that I designed back as a part of my master's thesis was somewhere in the realm of boosting 15 volts all the way to 6,400 volts. Okay. And in a space constraint that's around 90 by 95 mm, and the power rating was 10 watts. So the power rating is very low, and and I was trying to figure out which one works in my instance. Yeah, thank you.
Yeah, no, I think just to follow up, I think that sort of power range setup could be very, very good for the piezo transformers. Now, there's a lot to be done still to make the piezo transformers themselves, the design of them, practical. But I do think that would be a good application for that.
Very, very interesting question. Yeah, go ahead, Karthikeyan.
I also had questions on how one can go about. Probably not the right question for you, but
yeah, please repeat it. Please repeat. Yeah.
How can you hear me now properly?
Yeah. Go ahead. Yeah. Now it's clear.
Yeah. So how can one go about sourcing these piezoelectric transformers or materials, because they are not commonly found on any component suppliers website? So do you have any suggestions on that?
Yes. So first of all, I can say that we had the same challenge. Difficult to source the piezo transformers because they were very widely sourced, 2 decades ago or so when they were used in the lamp ballasts. But since then, because LEDs have come out, there aren't as many companies making them. And so one company we found is called STEM Inc., STEMINC. They have piezo transformers. It's a traditional rosin type transformer like the one I showed in the slide, the animation. Another company is called Transoner. Transoner does a radial mode transformer. Now, we have not tested either of these, but those were the 2 most promising leads that I could find so far, besides from having to make one custom. It's difficult, you're right.
I see. Understood. Because I think my research work definitely aligns with whatever MIT has done extensively, especially in the realm of high gain DCTC. Because we kind of had some of the works coming from Dr. Perrault and some of the works from Dr. Paulo Lozano. Yeah, so thank you very much.
Yeah,
Karthikeyan, before you leave, I just wanted to know which application needs 600 volt in that frame size. I just was curious.
So well, it's interesting because we are working on a special type of thruster known as an electrospray hybrid thruster. So these are thrusters which are like glorified cathode ray tubes which emit ions out instead of gases. which will help in propelling the satellites forward. So these are very high impulse, high specific impulse, low thrust applications which need very high voltages to operate. But the challenge is that satellites have a very low voltage power supply, somewhere in the order of 28. So we need to boost them all the way to thousands of volts range. Actually, Dr. This work, I think you can definitely find from the aerospace department's papers, especially by Dr. Paulo Lozano and Fernando Mir-Hicks. You can definitely read their papers. Dr. David Perrault has been the electrical lead, I assume, for those projects. So that's the reason why I'm asking you these questions. Thank you very much.
Very interesting. Very interesting. Thank you. Dr. Lalita asks, is there any advantage in using the same converter topologies that you showed for classical inductors and capacitors? Is there any advantage?
I would say no, because, well, at least for this one, for example, the reason why this is more complicated is because we have the capacitance across the piezo that we have to soft charge. That capacitance is pretty large, and so if we don't soft charge it, then we have a lot of switching losses essentially with the piezo. We don't have that problem with inductors and capacitors, and so that's why in a typical resonant converter, you can see we've got many, 50-50 duty cycle converters, constant duty cycle, whatever it be. Those are much simpler because the magnetic component in those converters can handle instantaneous voltage changes, while the capacitance in this piezo cannot. So I would not recommend these switching sequences with just inductors and capacitors.
Lalit, does it answer your question?
Yeah, that's fine.
Thank you. Shubham, please go ahead. You have lots of questions. Please go ahead fast. Shubham? Okay. He asks, does multiple switching stages affect the reliability of the power converter when you have the piezoelectric resonator? Reliability, that is first question. You can answer that, then there are more, at least 3-4.
I don't think that's a direct, I don't think there's a direct relationship between the multiple stages and the reliability. I think the bigger question with reliability is, again, how does that polarization of the piezo itself change over time? And also, how does it withstand its own stress and E field limits over time? But the multiple stages would be more of a reliability question for the control circuitry, for example, not the piezo itself.
Yeah. Follow-up is, he has typed it in the chat. Do you anticipate reduction in lifetime, because now you have a moving part, essentially, something that is at least vibrating or moving for long-term operation? That is his question. Now you have introduced something which vibrates. What do you anticipate the lifetime reduction? Will there be lifetime reduction?
There could be, but there are also ways that. I'm sorry?
Yeah, sorry, I was muted actually. So actually, Jessica, my question was something else basically. So let's say we use the converter for a particular application, just let's say for now X topology with this application, and then we are going with piezoelectric resonators. So do you anticipate any possible reduction in the lifetime of powertronic switches for long-term operation? So if I, let's say, measure the junction temperature for, let's say, for 5 years for X converter and the converter that you are showing here, so do you see any life cycle degradation in that aspect? Yes.
I don't think so, because like any converter, or I guess any traditional converter, each of these switches are on only one certain span of time per cycle. So the frequency, it turns on the frequency times number per cycle and turns off that many times as well. It's not turning on and off multiple times per cycle. So I think it should be about the same as other converters.
Okay. So the next question is about the control part, basically. So as you suggested that this is more on open loop control right now, but in order to have closed loop control, as I can see that, okay, the system order consecutively goes up with the number of elements that you have modeled here. So if you acknowledge this could be a problem, and of course a stability problem as well. So how have you planned anything to solve the closed loop control part, or started on that path yet?
Yeah, so we have been looking at closed loop control. It's initial investigation right now, and so we haven't published anything on it yet. But you're right that we do have to look at the additional complexity and of that control and see if it's worth it compared to a traditional converter. But I will say that we do believe there are solutions. They are more complex again than a traditional converter, but that's an excellent point. That's something that will have to happen for this to be realistic. We can't manually tune this in real life.
Right. Thank you so much. And just one last thing. In the last slide, I think you have mentioned that it is awaiting publication, but I think it is published, right?
Yes. So that paper is early access right now.
Early access?
Yes.
Yeah. Okay. Okay. Yeah, that's where I got confused.
Yeah. No, that's just.
Thank you so much.
Thank you.
Yeah, I think in closed loop, what would be your reference? I'm just curious on that. When you are trying to go for closed loop control, what would be your reference? I just had a question since.
Reference in terms of output voltage, or what specifically do you?
Yeah. So what are you trying to control basically?
Yeah. So if we take a look at, I'm going to go back to the waveform.
So it's like a regulator.
Yeah. So this will be a little bit difficult to explain. I do have unpublished material on this, but I can't show that yet. So what I can explain is that if we think about how long some of these switches are on, these switches are dictating how long our energy transfer stages are. And so, for example, this VN minus V out stage, we might choose to leave that on longer if we want to increase the energy that's going through the piezo in a single cycle. And then on top of that, it's just duty cycle and duty cycle and dead time tuning for the appropriate behaviors.
Good. Yeah, so it is really tough. Closed loop will be a challenge.
Mm-hmm.
Yeah. Karthikeya, go ahead with your question quickly. Please, we are almost over time.
Jessica, can you hear me?
Yeah.
Yes.
Yeah, okay. So I was just wondering, again, in the context of aerospace systems, that these systems not only have to be vibration tolerant, and piezoelectric crystals, generally, by the phenomena they work, are working on the phenomena of vibration. So what are the effects of external environmental vibrations on these systems?
Yeah. Very interesting.
Yeah, that's a fantastic question, and we actually get that question a lot. It's really important to think about. The answer is we don't know. We don't know yet, and so that would be something that would be really interesting to study, perhaps, because you're right that there are plenty of applications out there that, in terms of operating point, this could meet it just fine. But if realistically we can't deal with the vibration, or if it can't deal with vibration of the environment, then it's not practical. So. Yeah, I don't know. I think it would be really interesting to see, really interesting to study.
Yeah, that's interesting because, any aerospace engineer that I talk to, not electrical engineer, they're always interested with how much vibration tolerance a particular component has. And if for them to put anything in space, they really need that vibration compliance in place. And they were actually really worried even about putting ferrite cores sometimes. I think those were fairly inexperienced aerospace engineers, but ferrite cores definitely are brittle. So even that is a problem for them. And piezoelectric crystals might actually disturb the inherent phenomena in which they work. So yeah, it's interesting. Thank you very much.
Thank you. Great question.
Thank you, Jessica. And now if you have some time, you could go through. Did we leave any of the questions that were asked earlier? If you have time, you can just run through them quickly.
Yeah, certainly. Let's see. I'm pulling them up on my cell phone real quick. Okay. All right. So what are the design considerations to reduce EMI? And so that's the first question on this list. And so I can say that in terms of EMI, you can see that we're always soft switching and we're always soft charging. Oh, one moment. Let me get my batteries moving.
Others, please post your question. We're almost out of time, but we will take few questions.
Yeah, so we are always soft switching and soft charging, and so there is reduced EMI because of that. But we have not gone to the extent to measure EMI. We've not done an EMI filter or anything like that at this point. It's still very early. Okay, next question. What role will these topologies play in the integration of EVs in different forms and different applications with renewable penetrated grid integrated systems? What I can say about this is that this is going to shine more in the high voltage, low power applications. And so in terms of the bulk of the power transfer for an EV, I don't think this is the best bet to go with. I think a magnetic converter is probably better. But again, in situations for each of those applications where the voltage is high and the power is low, I think this could be a fit. What is the typical energy density of piezos compared to inductors? That's an excellent question, and that's something that we do study and we do talk about. In terms of a raw calculation, the energy density is about an order of magnitude. The energy density capability is what I'll say. So without considering thermal constraints and without considering other things, the physical capability is about 1 order of magnitude higher than that of an inductor. Now, this is, again, without showing many quantitative details, but that you can think of that as the estimation at low power.
Is it intuitive? Is this?
I'm sorry?
Is this intuitive? Is it an intuitive guess that it is an order higher, or?
That's a it's based on a calculation, a fundamental calculation.
Good.
But what I will say is interesting here is for the inductor, for example, we can pull all of the energy it stores out every single cycle. Whereas with the piezo, because it has such a high Q, we can only pull part of the energy out every cycle. We can't pull it all out. And so it becomes a question then of how much energy can we pull out and what's reasonable. And so we actually prefer to focus on power density rather than energy density for these specific applications for that reason.
Got it. Yeah.
And then it says, what are the drawbacks of this new technology? And so I think at this point, there are many. There's complexity, there's reliability, like we've discussed. There are lots of challenges that we will have to overcome before these are competitive with magnetic converters. But in my opinion, that's part of the fun of exploring something that's new, is because you have the possibility to really make something happen that seemed like it was impossible before.
So when you submitted this, was there any crucial follow-up question that the reviewers asked, which was really you had to think to reply back? When you sent it to publication, was there any significant question that was, or it was a breeze through?
We actually got very lucky and we were accepted on the first round. But
very good.
There were comments. But again, that's just a luck thing. It's very difficult typically. But the reviewers were very good. They had very good comments. And so I'm trying to think back to, I think a lot of the comments clarifying the theory.
Yeah. Good. Yeah.
Let's see. Our PR-based converters. Oh.
Yeah. Go ahead, please.
Are PR-based converters very expensive compared to those based on traditional energy storage? That's another really good question. I would say right now, yes, they would be. But over time, if we're able to continue developing them and bring down the cost, especially through batch fabrication of the piezos, or maybe even integration of the piezos, whatever it be, I think over time we could certainly bring down the cost and be competitive, if not lower cost than magnetic-based converters.
Yeah, I think it's good enough, Jessica. I think yeah, we are already over time. We'll not keep you any longer. We have few PhD candidates in the audience as well. Sivagami, can you please unmute yourself and introduce yourself, Sivagami? Yeah. Deepa Vincent. Yes, they're all PhD scholars. They were asking, looking forward to this presentation. Okay.
Great.
Nisha. Yeah. Yeah, I think there. Yeah, Shivagami. Yeah, please introduce yourself to Jessica. Fast. Hello. Oh, yeah, I think we can't hear you. She unmuted herself. Yeah. Now we can hear you. Okay. I think. Okay. Yeah, I think there's an audio issue at her end. She's working on wireless power transfer. So she was asking. Okay, we won't keep you any longer, Jessica. Thank you very much for such a detailed technical presentation. Very hard to find, and thank you for your time and such a short notice. I know you had many deadlines, so thank you for sparing your time. And on behalf of IEEE IES PELS Society Bangalore Chapter and also Women in Engineering Bangalore section, I thank you for your talk and for answering all the questions. Very good. Thank you for your time.
Thanks for having me.
Yeah. We're very fortunate and hope everybody gained a lot from this talk. Thank you, Jessica.
Thank you. Have a great rest of your evening.
You too. Thank you. Good morning for you as well.
Thank you.